Okay, so let's start. Keep it to within the time limit, please.
Just testing. Okay. Okay, so hi everyone. So today I'm going to present a paper called an off-chip attack on hardware enclaves via the memory bus. So this is the crude outline I will go over. So I'll introduce what the concept about this attack is, and talk about its threat models, and then the attack itself, and then I will summarize with the limitation as well as the future work and direction. So as you guys know that in the class we learned that hardware enclaves, they allow us to create secure area inside our systems so that the apps and data can be securely executed and computed without the tampering from the other outside untrusted system, which includes the OS and the other larger parts of your systems. But the thing is, like, we know that the enclaves will encrypt the data for us, but when they send out these data, including the address, these outputs are not encrypted at all. So this means adversary can basically snooping on this outputting address, and then starting making their own deduction and eventually get your sensitive data. So this paper brings up these problems along with threat models. So they named this attack called the Membuster, which is a pretty funny name to me. So what the Membuster is it's an off-chip side channel attack by just snooping at these outputting address from the systems you have. So basically, as an adversary, you will collect those signals from the outputting address bus line, and then you will collect all these signals and do offline analysis by interpret whatever the underlying memory access commands are involved. And by knowing the log of these memory access commands, you can start reverse engineering what the underlying associated address are, and then start to translate from one address to another address, and eventually you will get to the sensitive data the user hid from you. The adversary is assumed to know the following knowledge. So basically, they have to have physical access to the victim's device in order to do this snooping. And they need to know well about the victim's application as well as the runtime environment. So basically, the adversary needs to go over the apps the victim use, maybe just go through the source code, so even reverse engineering by themselves. And the runtime environments can include whatever libraries the victim use or the OS they runs on their applications. And Membuster and start with by setting up the snooping equipment. So basically, the research team did is that they're using interposers to repeat the address bus signals, and then they recall all these signals to their own devices so they can perform the analysis later. And they decided to using Intel SGX as subject for their experiments because SGX has best known security measure for the DRAM attack. So that's what the team decided to do. Once you collect all these signals, then they using the knowledge of all the common the DRAM memory access commands. So they using basically these for the activate, pre-charge, read, and write, and using these to see that all these collected signals how are they looking at by these four commands they know. And then they will have a log of all these sequence of the four major comments, so then they can see that what memory address are involved and what kind of access or action are taken on all these associated address they just collected. So once they know all these involved address, they will start focusing on the part where the DRAM address that's actually produced by the enclave itself. So in order to go over this translation overhead, basically they will go over the enclave page caches and see how these DRAM address are generated based on these sensitive data. And then they will also do the physical and virtual mapping acquisition at the same time. So combine all these knowledge together, they are able to translate the DRAM address they got by collecting the signals all the way up to the sensitive data the user decide to hide from everyone else. Yeah. So the strength of this attack model is you don't necessarily need to do all those on-chip manipulation like flush and reloaders or prime and probe, so you don't have to physically working on all those things. Instead, you simply just looking at the outputting that unencrypted address bus signal, which is a little bit less work than what they consider to those typical attacks, And these attacks can actually involve in both the edge devices as well as the cloud devices. So if you know where the server is, you can do it and temper the cloud systems. And if you know the edge device and you specifically want to working on the user's one, then you can also do that as well. But there are a lot of challenges here. Is since you're working on this huge roundabout, you start with the DRAM address and all the way back to the sensitive data, you need to do a lot of reverse engineering to know how to translate all these different addresses together. And also, since the DRAM request is fairly scarce when they collecting the signals, so they have to go over a lot of issues with the DRAM request, since they need to be able to generate more misses, cache misses, that allows the system to output more requests from the DRAM. So they have two major techniques for the DRAM. So they use critical page whitelisting and cache squeezing. So both of them are aimed to reduce the paging effect by the SGX systems, as well as increase the numbers of successful cache misses they can use to get the sensitive data on the users. And this is the diagram that shows the attacks implementations. So basically what they aim to do is they try to use the minimum amount of caches that allows you to get all the critical sensitive data by the users. So they do some pinning as well as mappings, and then they can illustrate this designs in a physical implementation like a custom SGX driver to do all this primings on the targeted conflict caches that will allows you to get the secrets from the user. And since they can get this information by doing those improving chances of getting cache misses from the DRAM request, but they still have to distill the information since you get a bunch of them. So they decided they're using a very intuitive way, just called the fuzzy pattern matching. So basically, you will try to see the patterns of the access behavior by the user, and then you will do some score evaluation and pick the higher score that resembles whatever the actual true mapping looks like. So then they will be able to decide whether they can deduce the corrected behavior from the user by using these score evaluations. And they're using two examples for the membuster. So the first one is a hunt spell. So this one is working on a spell checking service on the browser. So basically what the adversary will do is they will try to get whatever the document the victim's trying to do their spell checkings. And that happens by observing the spell checking process done by the Hunspell. And so basically Hunspell has all these functions to add the words into their hash table dictionary, and they can also look up the words they found to do this spell checking process. And then the adversary can eventually end up with the patterns that how the spell checking is done for the user document, and then they can tracing all these access patterns to figure out what the possible contents the user is trying to do the spell checking. And the other example is the main cache. So this one is a key value cache database. So basically trying to speed up the process for the server application. So what the adversary will do is for this email server indexing examples, they try to get the secret targeted email from the victims by observing the hash table access by the main cache. So the adversary will observe the key value that's being operated by the main cache itself, and then since the adversary is known what the pair, the key and the values looks like, so they will be able to see what are the words accessed by the systems when they go over all these patterns done by the victim themselves. And this is a small diagram showing that how the adversary can done this attack. So in short, that if you want to know some certain mails from the victims, you can just do some malicious emails sending to the victims, and then you let the main cache do the assessing of its hash table, and then you can using this process and distill the secret emails you wanted, including the contents inside. And this is the results of the two examples as shown by the research team. So basically they were able to produce a result that their main buster attack was able to get a pretty high recovery rate when they're trying to recover the secret contents, basically the word and sentence in the user-sensitive document. And the initial recovery wouldn't be too great without the assistance of the two introduced methods, which is the cache squeezing as well as the critical page-wide listing. And they test on different types of documents, so they have a random non-repeated word ones and a without oaths one that more resembles the natural language documents we see. And there are limitations for the membusters for sure. Since you can only access the DM requests in very few times, since they are the current modern CPUs has very large LLC, the last layer caches, so you don't have many times to see the DM requests from your systems. Which means that if you want to repeatedly access a particular address that contains a particular sensitive data, you want to know that, you have to wait for a while since the system is not going to give you the response as soon. And also, this attacks relies on a huge knowledge about the patterns that's generated by the victims. So if the victims critical addresses, which is the address range that contains their sensitive amount, is fairly small, and also the victim left very little footprint to tell them how do they access this knowledge on their own, then basically the adversary don't really have much evidence or clues they can find to do their reverse engineering. So there's a pretty high level of difficulties out there for the adversary to think about when performing such an attack. And also the paper focus on the analysis on the contents and address, but they also notice the timing issues and the traffic about this address output things can also be unpredictable based on the system's implementations. So sometimes you can have delays on the read and write back for those sensitive data, especially if you are the victims that like to dump the secret data as chunks of numbers or values. So this can cause some delays. So the future for these papers, they recognize that they didn't do too much about the timings and the traffic about all these like address bus. So they suggest, and which I agree that they can have the future team working on timing analysis so that they can know how this schedulings and the sending of the address signals can actually maybe provide more information for the adversary to deduce the knowledge rather than just solely relying on the contents and address they obtaining from the current models. And then the future team can also try to working on different hardware enclaves that's not mentioned in the paper. So there are a bunch of them, except in addition to the Intel SGX they're working on. And also there are actually some mitigations you can do for these systems. So like have the encryption and decryption model for your address bus. And you can also use oblivious ring to make your process and of the execution of sensitive data and code more opaque to the victims. But the future can work on to do some costs and trade-offs on all these available methods for sure. And that's all for the presentation. Any questions?
Yeah, questions anyone? So I think a couple of takeaways from this work. Firstly, the whole sort of address bus in a way acts as a side channel of sorts, and so and kind of encounter these kind of issues also in context of networks, like for example, examining where the packets are headed to or where are they going. This is the counterpart in case of processors. The other thing is, I guess, ORAM and all these are some of the methods that are being explored. So you could hide the address pattern. I guess one method really is to access everything so that the adversary cannot tell precisely what you're accessing, and perhaps randomize it. But ORAM is a kind of a theoretical concept, smarter way of hiding address information. There is also encryption of addresses, but that often messes up with the caching in the DRAM system. So there are kind of efficiency issues which come up with these systems. But in any case, I think if an adversary has access to the board and can probe lines and all, then there is all these kind of attacks which become feasible and potentially pretty problematic. Anyway.
Okay.
So in order to do the critical page whitelisting, I read that the authors had to kind of break the SGX driver. Is that something they can really do?
Remember, so the OS is the adversary, right? And the SGX driver, that is handled by the OS. So
even the driver is...
So the driver is not inside the SGX. That part is being handled by the operating system, so therefore it can still miss.
System call there was
so essentially SGX code has to rely on operating system for many of the services, and the idea is that if you don't trust it, then you need to handle it kind of yourself. But the problem is scheduling, paging, these kind of functions are still handled by the OS, and since OS is the adversary, so you have to assume that the adversary can still do that.
Okay.
So there are, for some of these things, there are attempts at literally running a small operating system within the SDA, so kind of a very lightweight thing and all, but it kind of begins to defeat the purpose, because if you end up making the code inside the SDA super complicated, then all the assurances you have about it being something probably correct kind of disappear. So you don't want, so the answer is not let's run a full-blown Linux or whatnot inside SDA. So there are lightweight libcs and stuff like that which people have created, but not the drivers or memory or that state.
Any more?
Great. Well,
Okay.
thank you.
Hello everyone, my name is Vyacheslav Indyryakin, and today I'm going to present to you paper number 12. Since automatic black box side channel synthesis on commodity microarchitectures. So my presentation will cover the following topics. I will give some words about motivation of this work. As an introduction, I will describe threat model. I will go through the algorithm, and in the end, I'll discuss strengths and weaknesses of this work and its future directions. So, introduction. As probably everyone here knows, operational systems running on today's processors provide strong isolation guarantees for processes running on them. As an example, we can remember memory isolation in RAM. So each process has its own memory space, physical memory space, and does not interact with others. It doesn't even know whether other processes exists. Oh, sorry, it should break my. Okay. But there is no real isolation guarantees for processes on the microarchitectural level. This means that due to performance issues, many things in many components of processors are used cooperatively by processes running on it. This includes caches, TLBs, execution ports, and many others. This means that by observing the state of this collectively owned elements of process of CPU, one process can gather some information, can gather traces of another process, which opens a door for an attack. So microarchitectural side channel attacks are presented majorly by eviction-based attack. What does this mean? By exploiting knowledge about microarchitectural structure, organization of a component, an attacker can put some element of the CPU in the known state, and in the known for the attacker state, and after target victim process has changed this state, an attacker can observe these changes and collect some information about the victim. What characterizes this attack? All of them are white box because you need some insights in the component's architecture you want to attack. They all component specific. So even if some this is the same CPU, but some bugs were fixed, you cannot probably run your attack, your malicious program on a new version of this CPU. They're hard to design because they have to because they require carefully hand-picking, cooperatively owned elements of the CPU. To gather, to find the most perspective from the point of view of collecting traces of another program. Which makes them hard to launch. This is why this paper introduces contention-based attack. Instead of putting the target system into the known state, contention-based attack just passively monitor cooperatively owned elements of the CPU. And by gathering this information, then they can deduce a secret from this program. They are less suspicious to programs that to systems that run some kind of malicious program checking on them because they do not change the state of the system. They just passively monitor it. So the threat model, as an input of I would say attack algorithm, we have a victim program in form of just code and microarchitecture. What does this mean, microarchitecture? This means an instance, live instance of target component. And as an output of the algorithm, we retrieve some secret key from a victim program. What assumptions are made? First and foremost, CPU is thought to support simultaneous multi-threading. To clear this up, usually we I would say in day-to-day applications, I think anyway, we are usually more familiar with temporal multi-threading. This means that we have one CPU that runs threads in key, where they replace one another, and it is made look like all processes are running simultaneously, but actually they do not. They run in key. And modern state-of-the-art CPUs, they support simultaneous multi-threading. This means that to increase performance, a CPU can actually perform several commands at a time, at one point of time. So another assumption is that an attacker can verify retrieved key. For example, he has a task of signing into some website or system, I don't know, and they can just try a retrieved password they got from the system. It is thought that the key is used for sufficient amount of time. So, for example, it encodes some long enough message, and malicious and victim code are executed on the same CPU, on the same core of the CPU. So, to clarify on that, what is simultaneous multi-threading? This is something like that. There are ports that receive from P0 to P5. They receive some commands from the processes, and one of the processes is spy process, and the other is victim, and they execute them simultaneously. So, why is this important? This is important because the algorithm starts with leakage map generation. What is leakage map? In this structure, commands. It was found that commands running on the one ports affecting execution time of commands running on the others. So by running some command A from spy process, we can influence execution time of command B that was run by victim process, which gives us a way to create a map of how how commands in instruction set architecture influence each other. So some of the commands do not influence each other. this is depicted as blue regions, and what does this mean? This means that whether attacker process runs this command or it does not, victim's command executes in the same time. So this is blue regions. But sometimes when we run, when attacker runs some command, it makes victim's command to execute slower. So, for instance, like here. And by knowing this difference in these latencies, we can, by measuring a difference in these latencies, we can deduce what command victim process is running, which gives us a way to retrieve the code, the secret key. So this leakage map is individual for each component. This is why we have to have an instance of this component at hand. But generation of this leakage map does not require us to know details of have some insights about microarchitecture of the component. We can treat it as black box. We took some CPU. We run all of the commands that are possible here in pairs, and this way we get this leakage map. So when we have this leakage map, we enter analysis phase. What this means? We take victim's code. We either manually or using script they provided add synchronization points to this code, and we start with some command set that is run simultaneously with critical sections of victim's code. We use special genetic-based algorithm to modify our command set that is used to retrieve the key. After we optimized it, we collect contention-based measurement latencies, measurements without synchronization, and we gather several samples, and then we train a recurrent neural network on the received data, and the output of this recurrent neural network will be actually the key we want to retrieve. So it looks something like this. There is a known target process. We put special instrumentation that is special synchronization points where target process starts to operate with secret key. These instrumentation points, when target process enters this critical section, they put in some bit of shared memory between spy process and target process signal bit. And after this, spy process also starts running their its commands by gathering latencies of commands run by target process when simultaneously spy process runs their command. Spy process can deduce the secret key. Now, when we have sorry. One more thing to say here. First that we are doing there, we optimize commands that we run simultaneously with target process. We do it by increasing reliability. So we know the key for now. We just run simulation. We know the key, and we maximize probability of getting this key by trying different commands in the recipe set. So we modify this and get a command set that maximizes probability of getting a correct secret key, no secret key. After which we turn off synchronization and run it again. So if you have a question about this part, ask, because it is quite hard. After we gathered this, why do we need to run the process, run the measurements without synchronization? Because in real life application, when we enter attack phase, we will not have an opportunity to synchronize ourselves with victim's process. So this is why we collect these measurements, and we train classifier to predict what was the secret key. And now we have everything. Now we have, so output of the analysis phase is recipe, that is a command set optimal to retrieve the key, and recurrent neural network, which allows us to process latencies, get with the recipe, and retrieve the key. So now in attack phase, we take these two things as an input. We run malicious thread on the same core as the victim thread. We collect contention-based measurements without synchronization because we can't provide it. We retrieve it. We classify these measurements with our recurrent neural network, and we get some result. Usually it is a bit noisy, so we have to fine-tune the result either manually or with some script. So what are the advantages of this approach? First of all, it is automated. It can be done with a script without all necessary digging into microarchitecture. It is faster than, it is usually performs faster than the algorithm designed manually. It is robust to interrupting victims process. So until we can ensure that our malicious process runs on the core, we can ensure that we either way get a retrieved key, whatever will be the schedule of other processes executing on the core. It doesn't, this algorithm does not imply that we have to have some knowledge about microarchitecture, the process. Interesting thing is about what this algorithm can do, what people cannot do. When humans design some spying algorithm, they usually pick one contention source, for example, I don't know, for example, cache, and create a cooperative, so make two processes cooperatively own this resource and gather contention measurements. But this algorithm can create contention on several components inside the CPU and analyze all of them cooperatively using this recurrent neural network algorithm. What are downsides of this approach? So First of all, it produces stochastic output. This means that output of this algorithm is something like a key, a secret key we want to retrieve. So we probably have to work with it manually or try it several times with different combinations to really get the result. It is still component specific, so we need to retrieve a leakage map for the component, and researchers that made this paper, they face the problem that sometimes you do not have comprehensive set of commands that the CPU can run. In this case, you cannot launch the attack. So you still have to have some knowledge about the component you are attacking. It is still when the malicious process can run with not only target process but some others, it cannot be done vice versa. So if algorithm is not running on the core, we cannot ensure that we retrieve the key, which is sensitive to interruptions of spy process. So what this basically what is takeaway of this slide is that it is not exactly like in a strict sense a black box attack. We still have to know have to have some information about the component we are attacking. So future directions for this work are heuristics for fine-tuning. After we retrieve secret key, how can we denoise it or alike? So measurements of more leakage maps to attack more CPUs, and generalize eviction-based attack using the algorithm alike. So this algorithm does not change state of the system, but we can design a similar algorithm that can, and then also retrieve latencies and analyze them. So please ask questions, especially about analysis phase, because it might be confusing.
Any other questions? So I think we can skip the questions, but I'll just emphasize a key takeaway out here, which is anytime we have shared resources, then the pattern of contention is leaking information. And if you have, I guess, in a system like this, we do need the ability to train. So if you are able to run the attack code under control setting beforehand, then you can train a model and then use that model in turn to attack time to kind of extract the secret. And this could be done for any number of things. So there are papers which make use of the fact that if a CPU has multiple ALUs or instruction execution units, contention among them, because oftentimes what registers they can access and all, memory ports, cache obviously. So there are a whole bunch of shared resources, and any time you have kind of two things simultaneously contending, then the pattern kind of is actually leaking. So that's the essence. I think it's a hard paper, so I know you to present, so thanks for doing it. Okay, let's move on to the next one.
Okay, hello everyone. My name is Ann, and today I'll be introducing protection, root of trust for I/O in compromised platforms. So I'm going to talk about the motivation behind protection, the attacker and system model, the details of how protection is implemented, the analysis of the possible security attacks that protection protects you against, and also the evaluation of the system. So what's the context? So we have secure and safety critical systems like e-voting and medical devices which require user interaction. Problem is the attackers have the ability to manipulate what the user sees on the screen. They can change the user input and also redirect user input to malicious websites. So the objective of protection is to prevent those things from happening. Previous works like Integrity and Fidelius have attempted to solve these problems, but they are inadequate. For example, Integrity, which is an external device that signs user input and then sends that to the server. The issue is it doesn't check what's displayed on the screen. So if you're on Venmo or something and you type 100, the display can read 10. So you might think, oh, I forgot to type a 0. So you enter another 0 and the display says 100, but Integrity sees 1000. So that's what it sends. And yeah, so that's the issue with Integrity. Another work which tried to solve this was Fidelius, which is another external device that makes an overlay of the secure fields. So the problem is the keyboard and mouse inputs are not checked. So it doesn't protect against redirection attack or clickjacking, early submission, etc. And also the secure overlay that Fidelius displays on the screen does not hide anything outside of it. So the malicious attacker can change the instructions and trick the user into doing something different. So because of those vulnerabilities, the paper goes into detail about what a secure I/O system must have to maintain integrity and confidentiality. The first requirement is interdependency between input and output. So that just means making sure the output displayed on the screen corresponds to the input typed. The second requirement is interdependency between all input modalities. So you not only do you use the keyboard to enter the information into forms, you also use the mouse to navigate through the fields, if you don't use the tab key, of course. Oh, but then, and you also use the mouse to click the submit button. So you must check both of those things in order for your web app to be secure. The third requirement is no cognitive load for I/O integrity. So that means while you're typing into the form, right? Ideally, you don't want the user to keep an eye on suspicious activity outside of the form. The 3B is related, user attention for I/O confidentiality. So again, that relates to making sure the user doesn't have to pay attention to the outside of the form to ensure that they're not clicking on the wrong thing. And then finally, the fourth requirement is small trust assumptions and deployability. So we want our protection system to be portable and easy to install, so you don't have to rely on hypervisors or trusted execution environments with huge code bases. And we would ideally like to not to install anything. So enter protection. So protection involves the I/O hub. So that's our main external device that so it takes in a form from the server and renders the secure fields on the user side. So even if the host has access to your computer, he can't see the form. I/O hub, he has no access to I/O hub, only IOHub displays and renders the form. So I'll explain the attack model. So let's assume the attacker can compromise the host. Like they have access to your display, your keyboard, your mouse. And they can also manipulate what the forms look like and even change what the user appears to type. However, the attacker cannot, of course, physically attack the IOHub. So imagine a hacker breaking into your computer remotely. Okay, so for our system model, I'll explain to you how it works. So you have a few agents here in play. So you have the server and you have the host. So the server hosts the web application. So first, on the server side, you have something called protection.js, which is a server module that takes in the HTML form elements and translates it to a format that's then converted into a QR code. So that QR code gets served to the host. Now, once the host receives the QR code, it sends the data to IOHub, which is our device, which checks the signature of the QR code and makes sure that it hasn't been tampered with. Next, IOHub renders renders the form from the QR. So this is important because our hacker does not have access to IOHub. So all they see is a QR code. Now they can decode the QR code, but that just gives them the form. Like they can't change the form or see what the user's entering. So yeah, whereas meanwhile the user can see the form. Okay, now as the user is typing into the form, our IOHub intercepts the keyboard and the mouse. So what the attacker sees is a frozen mouse and keyboard, like nothing's happening. Whereas on the user side, they see a cursor and keys and words being typed. Then after that, when the user clicks submit, IOHub signs the user data and sends it to the server. And if the attacker tries to submit it, like do an early submission attack, the signature won't match, and yeah. So I'll explain in detail what protection.js looks like. So protection.js, so it takes in an HTML specification of form and translates it into a JSON that contains form labels, sizes, text boxes, etc. And this is the part that gets translated to a QR code. Yeah, and the advantage of using IOHub and protection.js over, let's say, some browser renderer like JavaScript, is that it has a very small code base. Okay, so how do you go from QR code to form? So IOHub also intercepts the display. So you connect the HDMI to the IOHub, and it takes the QR code and then renders the form for you. Another security measure that IOHub uses is lightbox, which means blanking out the rest of the form and emphasizing the sensitive area. So even if the attacker manipulates this and puts credit card number, social security, whatever, it gets hidden, and only this part gets displayed, and the hacker cannot see this. Another security measure that you could also use besides lightbox is freezing. I mean, not besides, but in place of lightbox is freezing, which means basically freezing the rest of the form. So if the attacker tries to distract you with animations and other movements, then you can't see it because it's frozen. And finally, the overlay is protected with a secure attention sequence. So even if the attacker imitates the overlay, it will not be able to like activate unless you press the key sequence. So the paper doesn't really say how how the user knows the sequence, but one possible, but the sequence is encoded in the QR code, and that sequence activates the form and prevents the user from like entering the form when they're not supposed to. And then the last technical detail is mouse pointer tracking. So IO Hub starts with calibration of the mouse. It moves the mouse to the upper right corner, and then it starts searching. Okay, this figure is weird, but the paper says upper right corner. So pretend this is the upper right corner, and after calibration, it takes like a 200 by 200 pixel box and it searches it for a cursor, and then tracks the mouse that way. So if the IO Hub loses track of the pointer, then it redoes calibration. And notice up here, so the IO Hub activates its own pointer and keyboard system when the real pointer enters the QR code, or enters this area. So from the attacker's point of view, all they see is the pointer here and nothing else. But the user can see a real, or an IO Hub version of the pointer, and also all the form elements. Okay, so how is this implemented on hardware? So they use multiple devices. So here is the Raspberry Pi 4. It implements like all the logic of IO Hub, including rendering overlays and checking the signature and such. And then we have an Arduino Due, which is let's see, 3D. Yeah, this is the Arduino Due. So that one takes in the keyboard and mouse input. That way, the attacker cannot see your real keyboard and mouse input. Another device we use is Arduino Zero, which is this one, which relays the user input to the host. So if the keyboard and mouse are outside the form, then yeah, that's what you send to the host computer. But if they're inside the form, then this guy freezes the keyboard and mouse so the attacker doesn't see. And then finally, they have a B101 HDMI to CS2 bridge, which is this thing right here. That one takes in the HDMI input and then outputs a camera signal for the Raspberry Pi to read. And that one, is for QR code interpretation. Okay, so let's talk about various attacks that are mitigated by protection. So one of them is early form submission. With protection, that is impossible because the attacker, because IO Hub intercepts the mouse and keyboard movements, so the attacker cannot see any of that. And if the attacker tries to, click submit, nothing happens because IO Hub doesn't see it happen. Another attack is the replay attack, which is like resubmitting form. So the way you protect against that is for each form you have an ID, and a different ID. And if after the user submits the form and the attacker tries to submit it again, the server will see that the IDs are the same, and so the second submission will be ignored. And then the third attack is redirection. So one example of redirection is phishing. Protection prevents that from happening because when it renders the form, it makes sure that the site that's hosting the form is on its internal whitelist, and it uses a public certificate system. And another measure that prevents redirection is the SAS. So if the phishing site probably does not have the SAS protection on it. So here's the evaluation. These tables just show that the system is very fast. So it's a seamless experience for the user. Display latency is only 26 21.76 milliseconds. So that's still faster than 30 FPS. And then a big advantage of IO Hub. So instead of using a browser or a whole OS to render the form, you just have your protection.js, and that's really small. So yeah, so that's protection. Do you have any questions? Yeah.
Could you describe the data flow that goes from the server into the IO Hub? Does it go through the host?
Okay.
Like,
Yes. Okay. Quick answer is yes, but let me go there.
right.
Yeah. So the server sends the form to the host, so like the attacker can see the form. But the host also sends the form to IO Hub. So even if the
But how does the host? Oh, the host sends the form to them. Okay.
yeah, so that's like your computer that's being attacked. Yeah. So yeah, even if the host manipulates the form, IO Hub will sense it and like invalidate it.
Oh, okay.
Yeah.
No, so how does that happen? I'm not sure. So if the attacker on the host manipulates the form,
Yeah.
how does the IO Hub know that the form is manipulated? Because, like, how does it do it?
Some key has been like.
I think you missed some critical details out.
Yeah, there's
Yeah,
like a key pair is generated and the server verifies against that. So if the attacker manipulates the
Exactly,
that key is
yeah.
not gonna match something.
I think you have not described the relationship between the server and the IO Hub, because otherwise in your model simply the attacker does anything, IO Hub is not any wiser.
Yeah, so that's why I made a quick mention of like how like the IO Hub checks the
So how does it do it?
Oh, so there's like a connection
Yeah, there's
between the
a-
two.
yeah, TLS.
And they
Has a
establish a
connection to
key.
the server. Yeah, there's like a.
So then why can the IO Hub not be attacked? Like, in the sense that there has to be something special about IO Hub if the host can be attacked but not the IO Hub, right? So if IO Hub is like any other computer on the network, then why can the IO Hub not be attacked?
I mean, IO Hub is a physical device.
Sure, so is the host, right? So what is it that makes host attackable but not the IO Hub?
Yeah, they're considering the host as that.
Huh?
The host is that person.
Right. Well, or the host has been compromised.
Yeah.
Okay, but why can the IO Hub not be compromised? What is special about the IO Hub that it
Well,
cannot be?
it can actually be compromised. They did mention that it's not.
They assumed it wasn't.
Yeah,
They
that's-
said that it's not.
They did say that they didn't.
No,
make
but the thing that you are trying to solve is voting machines and stuff like
Yeah.
that, right? Your host is presumably some machine in there, and then IO Hub is where you are actually doing things, right? So what is special about the IO Hub in this model that attacker can presumably attack the host over the network? Why can it not attack IO Hub?
It can actually. They did
So
mention
then
that,
what does
they did mention that it's like the host can simply like do a denial of service attack to the IO Hub and like render it useless and everything. Yeah.
No, there has to be. I think there's some point which is not coming out, because if IO Hub is just yet another computer,
Well,
on the-
it's not
on the
connected to
network.
the network directly. It's
But
connected
it
to the
is.
host. It's connected through the host.
Actually, this diagram is showing it is connected.
No. It's connected through the host. They did mention that it's not directly connected. So the host is basically acting as the network. element.
Okay, so then why can the attacker once it's on the host not attack the IO Hub?
It can actually.
Okay, I think there's some point which is being missed. I don't know.
I think
There's-
that's a flaw in the paper because they directly say, we assume that the IO.
Yeah, they said that we assume that it can be.
And
Yeah.
then they go on to say, that if they wanted to explore securing the IO hub, that'd be another piece.
So that they'll make like a
Yeah, they said-
secure hardened version or something like
Okay.
that.
One assumption I forgot to mention is like, let's just pretend that all of these devices are trusted. Like, that those devices have not been compromised. So that's one assumption that they make. And yeah, the issue works quite free to address this issue.
There's also another problem with the IO that the developer of the website needs to annotate, I think in HTML, like the sensitive elements, like protect equal to true, something like that. So if that's
You have to
not-
design the pages.
Yeah, so
for-
basically the web page needs to be designed in a specific way.
Yeah.
For-
Yeah.
So I think the reason I kind of selected this paper is the following: that I think there's a whole bunch of applications where this issue that an adversary is able to attack users' interaction with your device. Okay, so even trivial things like we often take photos of a document. Okay, how do you know that? And you see the correct document which you just scanned, but the one which is going out is not what you scan. Or like you press OK button, but kind of the attacker is able to. So this attack on kind of the user's interaction with the software, particularly in settings where you have a legal contract of some form or some other critical thing being done, is kind of pretty pernicious. So. Or like we took a screenshot and I'm sending that out. Is it indeed what is going on? So I'm seeing a fair number of papers which are kind of focused on that interaction. I think in context of e-voting, there have been complaints and all in some elections that, you know, I pressed whatever candidate A, but the screen kept on showing as if I was selecting candidate B. So these kind of things which are, and it turns out that until fairly recently, actually, in Android, they used to have this thing called accessibility interface. It basically, if you give certain applications permission because they were meant for assisting people with visual challenges and whatnot, so essentially those apps would take over the communication between an app and the display part. So like every event and every display action. And the idea was that these would be applications which will somehow help in an assistive setting. But they were also particularly privileged in basically attacking that interaction, right? They could, your application thinks it's displaying something, but this thing would intercept and display something else. Or the user thinks it clicked here, but this application, this accessibility app intercept and do it. So, so I think a couple of years ago, finally Google kind of disabled that capability and kind of no longer allows applications to essentially gain that accessibility mode. But that was kind of a big risk. So, so I guess long story short, I think this protecting the I/O interaction is something is non-trivial, and I'm not sure the solution I necessarily buy, because it seems like they're just kicking the can a little bit further. I've seen some work where they make use of the trusted enclaves, so SGX or TrustZone and all, to assist in this process, together with asking the user to do certain things like gestures and things like that. So you kind of have the app engage directly with the user to bypass something which is so in any case, thanks. So let's move on. I think we're running short of time, so thanks.
Hello, my name is Eugene, and today my presentation is about on the resilience of biometric authentication systems against random inputs. So this is my outline, and first I'll give a brief introduction about human identification and authentication systems, and then I'll look into biometric authentication systems, which are mostly machine learning based. And then I'll talk about the attack API and threat model for this specific paper, and finally the experimental results. And finally, I talk about some mitigation techniques that can resolve the problems that are seen inside this particular attack API. Okay. So human identification systems have been around since the 1870s, and during that time, it was mostly based on certain quantities that were able to be measured by the human body. For example, the weight of someone, the height, and etc. Nowadays, it's mostly based on digital signals, such as the photo on passports, fingerprints, the retina scans, etc. The difference between biometric authentication systems and these human identification systems is mostly on the automation. So in these kind of biometrics, we often use digital computers to process the input, and the models are often, as I said before, as a machine learning kind of model. And for these kind of biometric systems, a commonly used indicator of success is called FPR, or the false acceptance rate. So what this means is that basically you want your model to have as low
as low the FPR as possible, because this FPR basically represents the probability, the rate that your model creates a false positive. And since you want to authenticate the actual correct user rather than an incorrect user, you don't want any kind of false positives to happen inside your model. This is a brief timeline of a certain company that specializes in this biometric systems. It's called NEC, and it's a Japanese company. You can see that from 1971, they started using their fingerprint technology, and from the past 2 decades, you can see that they have more and more achievements that are commonly, they have more and more achievements. And in fact, even the government has tried to jump onto this bandwagon, and therefore this biometric authentication system is a very, very important field and very widely used field inside our current environment. Okay, so a basic biometric system can be separated into 2 phases, and the first phase is called enrollment or calibration. So what this means is that in this phase, they basically initialize your model, or you store your model with the correct users. So after you capture this biometric, whether it's a photo or a fingerprint scan, you do some processing, which could be also called feature extraction, and then you store this particular feature vector. And afterwards, if you want to do verification, you just go through the same capture and processing stage, and then do the comparison, and whether it's a match or no match. And in this specific paper, we only talk about binary classification. So it's always a match or no match. It doesn't output something like a probability, a spread of probabilities between multiple classes. Okay. So the question this paper is specifically trying to answer is that, is FPR actually indicative of the correctness of your model? So FPR is often used, basically it's often used as a measurement of your machine learning model. But when you consider the impacts of an attack inside your specific security hardware, then this is no longer accurate. Because FPR is basically trying to say, given a certain specific input, whether the output is correct or not. And this implicitly assumes that the attacker or the adversary can only manipulate the input of your entire system flow. So they can only change your inputs, but during a specific hardware attack, they can in fact inject the data between these stages. So they can either inject a raw image between the capture and the process phase, or they can also inject a fake feature vector after this process phase to do the comparison. So when you consider that, if certain services are hosted on the cloud, then they can do this injection between the 2 phases. And if your device is compromised, then the same thing can also happen. So intuitively, the idea is that for a certain specific feature, the distribution of their value should be somewhat of a certain distribution. So for here, it's assume that it's a normal distribution. So you can see here for the target user, the value for this one feature, which is extracted from the face recognition data sets, is spread around 0.1 to 0.5. While for other users, it's around 0.2 to 0.8. This means that for certain features, you can see that this range is in fact not used. So when you do the machine learning training phase, when you do the trying to reduce the loss, it actually does not have any inputs that reside within this specific phase, this specific bins. So when you do a certain kind of, so what happens when you try to inject a sampling that is uniform and random? That means that certain samples that you inject will in fact be situated inside these specific phases, and your machine learning model isn't trained for these phases. So the output could be either way. It could predict that your results are the correct user. It could also predict that the results are not. So what this means is that the actual acceptance range of your classification model is much larger than the true positive. So that means that even if your FPR of your model is small, the actual amount of false positives is large. So the assumptions for our model is that the adversary which wishes to find an acceptance sample, which doesn't have to be a true positive sample, as long as the classifier returns an accept or a pass. That means that the adversary can directly inject their features or their raw input into the hardware rather than changing the input from changing your data from the input of the entire system. We also assume that the attacker does not have any knowledge of the underlying biometric system, which includes the feature space, the user's past samples, or even the actual classification model that you're using. So for the first models, they process the results on 4 different data sets, including the face recognition, voice authentication, gait authentication, which is trying to predict the activity the user is currently doing, whether it's walking, running, walking upstairs, walking down some stairs, and the cultural swipe authentication. And each metric is assembled with 4 different models, including linear SVM, radial SVM, random forests, and a neural network. And as I said before, we can have 2 different injection points. One is before the feature extraction, and before the feature extraction, where you input the raw, inject the raw input, or after the feature extraction, where you inject a raw, a uniformly random feature vector. Okay. Yeah, and so the details of the data test, the data sets are shown here. Yeah, so for these 2, they took the pre-trained model instead of training their own model, and they use these models, and took the. So they didn't actually take the models from these previous works, but they trained their own models. And they specifically mentioned that they had similar results from the similar accuracy and precision from these previous works. And then they did their testing on their own models. Okay. So the results here show the spread between the equal error rate, which is when the false positive rate is equal to the false negative rate, and the acceptance region. So this is for the gates data set. That's for touch, face, and voice. And the 4 different models are shown here. It's linear SVM, radial SVM, random forest, and neural network. You can see that for the gate data set and touch data set, there's basically no correlation between the error rate and the acceptance region. While for the face and the voice, the only model that can be said to have some correlation is the neural network. So even for random forest, which should have a good result because it's ensembling and doing the bagging, it doesn't have much of a correlation. So even with low error rates, your acceptance region is huge. So that means that we can't identify the cause of. So since this paper is trying to minimize the size of your acceptance region, you can't just use the error rate of your model to try to modify your region. So the next step, so the observations are just what I've said before. the SVM types have large AR irrespective of FPR, which is basically shown here. Yeah, and the average AR is either higher than the FPR or at best comparable. So that means that basically the FPR is not a good indication of the size of your acceptance region. So the next step would be trying to identify the actual variables that may cause the changes inside the acceptance region. So what they did was that they synthesized the data set where each feature is normally distributed, and they basically did a lot of steps for each feature in order to make sure that these features are both normally distributed and random. And then they tested it on the same 4 models as before, and they tried 3 different modifications to these to the features inside. So the first one, they call it variable isolated user variance and fixed population. What that means is that they, for the target user, which is the true positive data samples, they increase the variance. And for the other false negative samples, they just kept it constant. So after this kind of manipulation, they noticed that the acceptance region increases as the variance increases, which means that it does not help shrinking the acceptance region. For the second experiment, they did the opposite. So they kept the positive samples constant, and they changed the variance of the negative samples. And I noticed that the AR decreases as the variance increases. So what this means is that as long as you have a larger variance inside your negative samples, then you can decrease your acceptance region. And intuitively speaking, this is kind of trying to determine the envelope of your inside the feature space of your positive regions. So if you increase the variance of the negative samples, you're trying to shrink your acceptance region such that it almost overlaps the true positive region. And finally, by increasing the population, they have a minor decrease in the acceptance region, which they believe is because basically adding extra negative samples and having a similar effect to the second experiment. So from here, they can see that the way to decrease your acceptance region is by increasing the number of negative samples. So, but what they notice is that since the samples are acquired from the users, you can't modify the variance of your data. So what they did is that they artificially introduced these extra negative samples that are spatially situated nearby the positive samples. So they basically generate noise vectors around the positive samples using the Beto distribution. So with symmetric noise. So what that means is that they basically generate these noisy samples around the positive samples with equal probability around every single dimension. And they label these extra samples as negative classes. So that means that they basically increase the number of negative samples. And then they did the training. And from the results here, you can see that for all 4 different models and all 4 different data sets, if you just do the normal training without mitigation, you can see that the acceptance region has no correlation with the FPR, the error rate. But after you do mitigation, then most of the acceptance regions decrease, while the most significant decrease is within the gauge and the touch data sets, which are, if you remember from before, the ones that have the most, that have almost no correlation between the error rate and the acceptance region. Yeah. So that's it. Are there any questions? Yes.
Yeah. Can you go back?
Yeah, sure.
Okay. Can you go back to the mitigation techniques, the slide right before? Yeah. So do you know if these FPRs are derived from the equal error rates?
So the equal error rates are when false positive rates are equal to the
Right.
false negative rates.
Right, so
It's
is
a-
that what this is? So the FPR
Yes.
should equal FR?
Yes, yeah. So for this specific paper, they just use these interchangeably. Yes.
So what about like the case for like multi-class classification or something like that? Like naturally the acceptance region is going to be much tighter
Yeah,
during those cases.
But I don't think the multi-class model actually fits using these kind of authentication systems, since it's either
No, they do, right? I mean, you can have multi-user like come in, it's authenticating among
a multiple a group
multiple
of
users. But I think the concept generalizes, right? What you want is that around each one of the valid users, you should have negative region and not leave it unspecified. I think the problem fundamentally out here is that in normal, like if you're doing activity classification, things like that, you can get away with essentially an under-specified system and let the decision boundary fall wherever it may. Whereas if you're doing authentication of any phone, unspecified should mean
Negative.
failure,
Yeah.
negative, yeah. That's really and I know like one of the groups is doing a project around making sure that the device is still on the person and all. I think these kind of issues are important in those systems also. So you can't, when you are just doing a normal classification, you approach lack of data differently than something like this. So I think kind of important takeaway. I think just generally when you're designing a system where it's going to give access to any sort of critical resource, one has to think differently about the classifier. Anyway, let's move on. Brian.
Thanks. We have like 22 minutes.
Okay, all right. All right, hello everyone. Today I'm going to be presenting Oculock, which is from NDSS in 2020. It's about how do you create an authentication mechanism for VR headsets. So nowadays, we know that with VR, you can do certain private operations. So for example, you can enter your credit card information in, you can check your medical information, and in the case of like top secret military applications, you can have pilots who are trying to crew these top secret aircraft. Now the issue out here is that classical methods for creating input in these VR systems rely on these either your movement of your head or the movement of the controller to input things in. And prior work has shown that anyone who is observing these activities can actually interpolate what is being placed on the keyboard. So basically so whatever observers out there, they can try to figure out what the input is. So the question out here is, can we create an unobservable VR authentication? That is, from someone who is standing outside of the, who's standing outside in the physical environment, can we make it so that they can't tell what the person is actually inputting? So there's some prior work on authenticating via what they call the human visual system, so basically your eyesight. They call them eye gaze biometrics, which focus only on the eye globe. So here you have a picture of the actual eye, and the eye globe is just constituting the eyeball itself, where you're trying to authenticate determined by the directions and how your gaze is shifting around in a particular system. So the observations behind this paper is they want to find other physiological features for the human visual system, and they also want to establish a method of measuring these features. So the problem out here is that even if we want to measure these features, we can't use something like eye trackers or high-res cameras because they might not work well in these particular environments. Okay, so here are some of the features that they want to focus on. So the question is, what parts of the human visual system can be used to identify people? They're trying to look for these characteristics that are unique across populations. So some examples include the opening and closing of eyelids, which shows that there's distinct muscle strength in eyelids, which differs from person to person. There's also changes in the eye globe rotation limit, And this is also varying from person to person. In addition to that, we have metabolic rates of the retinal pigment epithelium, which just shows that there are unique levels of activeness in the cells that are right behind your retina. So these are essentially performing, they're transferring nutrients into your eye, and they're also disposing of waste. And there are also more behavioral features, such as the scan path of the eye globes. So they characterize these as two categories called fixations and saccades. So fixations are sessions of stationary gaze, and saccades are the periods in between them where our eye is moving. So now that we've defined some of these features that we're interested in, the question is, how do we measure these features? And the method they propose is called electrooculography, which I'm going to refer to as EOG from now on. And what it does is it measures electrical voltage variance between the two electrodes. So you can place electrodes on different parts of or skin around your eye. And the idea is that there's an electrical potential that exists between the cornea and your retina. And by measuring how your eye can move, we can also measuring this standing potential. So the way it actually comes from is that during the metabolism of the epithelium, it causes this sort of electrical potential field. So how does the EOG measure these features? So as the eye moves, we know that the potential can change, because if we are changing the rotating angles of the eye, depending on where we place these electrodes, for example, in this work, they're placing one on the forehead, two, one and above and below the eyes, as well as near the temples. So during these blinks or other eyelid movements, there's a steep rise and fall in the voltage. And in addition, depending on where you are looking, the voltage potential will also change. And lastly, the metabolism also affects this voltage variance. So when we were thinking about using EOG to measure these features, here are some of the examples that they use. So if you want to calculate the eyelid close speed for using EOG, they're represented as these peaks in the EOG signal. So for example, right here in the bottom right, you can see a figure of, this is a post-wavelet transform of the EOG signal, but you'll notice that the blink will have a steep decrease in the electrical, in the voltage, and then it'll shoot back up again. So this is how they characterize the blinks. And for the eyelid close speed, it's just the slope of the EOG signal during when this peak comes back up. Then another example is, how do we try to figure out the metabolic intensity? So remember, the epithelium is the metabolic process behind the eye is sort of unique across people. So what they do is they calculate something called the Arden ratio, which is a positive correlation between this metabolic rate and the actual which is a positive correlation with the metabolic rate. And it's derived as the ratio between the maximum and minimum absolute values of the EOG signal. So across all of their tracked signals, they just take the maximum and then they take the minimum, and then they figure out the ratio in between to derive the Arden ratio. And here are two of the behavioral ones that we mentioned. So after we've had this wavelet transform to identify the signal segments, we can now pull out which are the saccades and which are the fixations. And using these, we can also determine when the fixation start times and the end times are. So now that we've defined these features and we can measure them, the question is, how do we trigger these features for authentication? So the method that they come up with is just like 3 different forms of visual stimuli. So the first is called a fixed route, where the person wearing the VR headset will see a red spherical ball moving across their screen in the directions that you see above. And the idea here is that it's to see what the limits of your globe rotation are. So even though all the users have the same scan path, each person might have different globe rotation limits. And in addition, during this movement, the user may blink, and they're also trying to capture that as well. The second visual stimuli is called the city street, which is a static image of a 3D city environment. And it's more of a behavioral tracking mechanism to see what aspects of the image the people are looking at. It's to measure what the viewing preferences are for a particular person. And lastly, the illusion is essentially a set of vortexes which are expanding and shrinking in shape. And it's similar to the fixed route stimuli where you're trying to see what the user is looking at any particular time. But apparently these vortexes elicit more movements and blinks than you would find in the fixed route. Okay, so coming to the authentication decision. So we talked about how we can present these visual stimuli, and from these we can now measure the EOG, and then from that we can measure these different features. So coming to the authentication, we want to compare the input EOG to an authorized user. So similar to the last presentation, there's already been an enrollment phase where we have a set of authorized users, and then we're comparing these authorized users against a new input set of features. And now we want to determine the similarity score. And these are a set of different models and comparison algorithms that they're using. In the end, they come up with they choose to use the A/B test as the final comparison algorithm because they find that the equal error rate performs well on that one. And before I jump into the experiment, they also push forward this threat model. So how do adversaries attack this particular system? The assumption here is that attackers will not install anything in the head-mounted display, and they also won't have any hardware on it for capturing signals. And so two attacks that might emerge given these constraints. The first is the impersonation attack, which is very simple. And the attacker is just attempting to authenticate using their own EOG signals. And the second attack is called the statistical attack, where the adversary has these statistics from a population similar to the user. So for example, if they're trying to capture EOG signals similar to me, they would look for a population of college males or something similar. And from that, they would essentially create a distribution for each feature, sample from it, and then create new EOG records given this distribution, and then inject the signals into the authentication code. So the experimental setup and study. So what they're using for the head-mounted display is called a Lenovo Mirage Solo, and the RG measuring device is called the BioPack MP36R, which has 200 hertz sampling rate, and it has 5 leads, as we've shown before. So they ran a study with 70 different participants where they set aside 35 for training and then 35 for testing. So what they did was they would provide each of the visual stimuli for 10 seconds to each user, and then they would repeat this study 10 times, and then resulting in 10 records per person. And the models are then trained comparing any 2 records across people. So it's similar to the binary classifier that we mentioned before. And the idea here is that we're using equal error rate as a metric for these final results. So this is the results for stimulus time versus equal error rate. So the idea here is, depending on how long we've exposed the users to these visual stimuli, what is the equal error rate? And you notice that the city street is actually the highest equal error rate, and that's not quite surprising because these are preferences that are going to change over time. And the fixed route and the illusion, okay, so the illusion actually performs the best out of all of these. Another question that might come up is that are these physiological features stable over time? And in addition, are these behavioral features going to be stable over time? And they also decided to measure this across a 2-month study. So what they did was they measured these, so they would repeatedly give these authentications back to the user every 3 days. And over time, they noticed that the behavioral features would sort of degrade the equal error rate because, as you would expect, these people would change their preferences for how they view this, how they view the images. And in addition, you'll notice that these physiological ones are relatively stable at around 10%. And lastly, as we mentioned, there's the impersonation attack. and the statistical attack. So during this impersonation attack, the thing to take away from here is that it's easier to create an attack over the city street stimuli, mainly because the way the stimuli is set up. So if the user looks at this stimuli, there's going to be a period where they're looking across the image, but then over time they might begin to focus only on one particular part. And yeah, as you would expect, the more physiological stimuli would perform better than the actual behavioral preferences. Yeah, that's all I have. Any questions? Yes?
The system usually takes a longer time for authentication than the others, like PIN-based or password-based. So why do they say that this is, should be preferred, especially in terms of reliability, when both PIN and password-based authentication systems are equally reliable and take lesser?
Right, so this goes back to the first problem, because PIN and password authentication mechanisms using a VR headset, they would require you to do some kind of input either with your remote or with your head. So,
Which would be observable.
right, which is observable by other people.
This is not easily observable.
Right, right.
So did they mention, aren't there way, I've seen some of these work where by using EMG and all, that let people sort of flex fingers and all and to kind of type without actually having a keyboard and all. So in effect, can you not make keyboard entry on the VR world more imperceptible? Like flexing muscles and things like that, which would be harder to observe?
Yeah, I guess that could work. This work doesn't mention anything about that, but.
But basic problem they're addressing is that
right, trying to get rid of this perception
the
of
perceptive,
right.
I mean, someone else nearby should not be able to figure out what you are typing.
Right.
Or whatever.
Right. Yes.
Will the authentication system still be effective if, say, you have allergies or you're affected by falls, so you can't really...
If you have what?
Allergies.
Oh, allergies.
Yeah. Well, I mean, or your eyes somehow.
Oh, that's actually a good point, because that should cause a change in the physiological signal. For example, how fast you can close your eyelids are going to be different depending on the injuries that you've sustained. Yeah. Any more questions?
So is there a challenge response component in this thing, in the sense that is it simply that they are observing how one is behaving, or is there still a component where I need to know something in order to be able to authenticate?
No, this is purely they show you something and they're trying to measure how you react
how you
to
are doing it, right?
Right.
I mean, so there's no, so it's not, it's purely relying on it's a biometric system as
Right.
opposed to a system which requires me to know something and then in response to,
Right.
because the keyboard system and all they're comparing against are
Right.
stronger.
These
in
are-
that
these are
regard,
active,
right? I mean,
yeah.
they have the factor of a knowledge.
Right.
to it.
Right.
So like in their illusion and all, it's not that I'm reacting to some
code that I
specific
know,
code
right.
that I know and
Right.
therefore I'm reacting to it. That's not.
It's not,
there.
yeah. Right.
Yeah. Anyone else with questions? Great. Thanks.
Yep.
So see you guys on Tuesday.